We've just finished our scaling analysis of the Navier-Stokes momentum equation for flow on a rotating planet. We've seen that this reduces to the hydrostatic balance in the vertical direction, and that the horizontal velocities are balanced by their respective normal pressure gradients, which is known as the geostrophic balance. These equations are often written using F, the Coriolis parameter, which is 2 times the locally vertical component of the rotation vector, omega sine theta. Note that F changes sign across the equator, meaning that the pressure gradient in a given direction is going to be balanced by opposing flows whether you're in the northern or southern hemispheres, which is the reason why cyclones, hurricanes, and ocean gyres flow in opposite directions for the northern and southern hemispheres. Now, these equations represent the leading order balance of flow in the ocean and atmosphere, and here we're going to examine some consequences of this geostrophic balance. One obvious application of the geostrophic balance is in trying to understand and predict weather. Here is a map showing sea level pressure from a weather model. The contours are isobars which connect points of equal pressure. The pressure changes as you go across an isobar, so the pressure gradients are oriented normal to these isobars. Now, our geostrophic balance suggests that the pressure gradient in a given direction will be associated with a wind in the normal direction. That is, the winds will align with these isobars, which are normal to the pressure gradients. Taking a quick look at the surface winds shows that this is indeed the case. It also shows that the wind speeds, which are represented by colours here, are largest where the pressure gradients are large. Stronger winds are associated with stronger pressure gradients, as per the geostrophic balance. An interesting point to note here is that the direction of the winds are also given by the direction of the pressure gradients. These high and low pressure regions have winds that are circling in opposite directions. However, in both cases, the winds are oriented such that the pressure decreases to their right. Another application of the geostrophic balance can be found in the ocean. Consider an ocean in XYZ coordinates with a depth h0 and a surface pressure p0. Let's say the rotation is anti-clockwise, so we're in the northern hemisphere. Now imagine that h, the ocean depth, is a function of y, so that the free surface here slopes down towards the right. From the hydrostatic balance, the pressure anywhere in the domain is simply a function of the water depth h and the atmospheric pressure P0, which we can assume is constant throughout our region of interest. Now we can differentiate the hydrostatic pressure equation in y to get an expression for the change in pressure in this y direction. So on the right hand side, the only term that has a y dependence is h, giving dp dy is equal to rho g dh dy. This horizontal pressure gradient term is the same as the one in the geostrophic balance, so that we can make the substitution and cancel for density and rearrange for u, giving us u, the velocity in the x direction, as a function of the free surface slope in the y direction. Now it turns out this is a very useful relationship to know. Free surface slopes are something that can be readily measured, particularly with satellite observations, and through this geostrophic balance we can get some meaningful information about the velocity field from a measurable quantity.